Hey everyone, welcome back to my daily coding series. This episode is 94. So this is my second recording today, so hopefully I can get through it with my remaining brain power. So this is a hard graph problem called Alien Dictionary, so I just skimmed through it a little bit and thought it might be fun. Up until that, I haven't looked at it, and this is going to be like a live problem solving video. It's not a tutorial or anything. All right, so let's look at it. So it's called Alien Dictionary. So we're given, there's a foreign language which uses the alphabet, but the order is not A, B, C, D, so it's not the traditional order. We get some words which are sorted lexicographically based on the rules of the new language. And we must determine the order of the letters. So using a couple words which are sorted lexicographically, we must determine the order. And we have to return any valid order of the letters that have appeared. There could be multiple answers, and we can return any one of them. So we don't have to return all of them, which is nice. Yeah, so that's the gist of it. And also just something to keep in mind, it also could be impossible. So if it is impossible, then we need to return an empty string. Okay. A string A is lexicographically smaller than a string B. If either of the following is true. The first letter where they differ is smaller than A than in B, or there is no index I such that A of I does not equal B of I, and the length of A is smaller. So this means like if you have AB and ABC. So this condition is true, and there is no index I where A of I does not equal B of I, assuming that I is in range. If you have I kind of just like know what lexicographically smaller means, but the first letter where they differ is smaller in A. Oh, okay, yeah, that makes sense. So the first letter that they differ. All right. So I could see how we could use a graph. So for instance, in the first example, we give two words, Z and O. And we know that these are sorted, so we know that the word Z is smaller than the word O. So we return the letters sorted, which is ZO. So that's a pretty easy example. If we look at them, I'm glad they give us another one, or else this problem may have been a lot harder to understand. I'm not going to do the quotes. We don't need the quotes. So we're going to do HRN, HRF, ER, ENN, RFNN. Okay. So in this case, we know that this is the smallest. So something that I know by looking at it is we compare the first letters of all of them, and we see that H must be less than E, which must be less than R, just because, H's come first. We can look between the H's, and we see that the R's are the same. So now N must be less than F. We know that. If we look between the E's, we see that R must be less than N. And here we see that R, well, I guess we can also, is it true? So my question is it true that we can derive that E is less than N? Because is each word sorted? I don't think necessarily. Oh, it gives me a... Okay, it doesn't say Yeah. So we don't know that this, so this itself is not sorted, so we can't derive any information from the word itself, only the ordering of the words. So we know that R is less than N. And then here, I would say we can't derive anything, but it says from ENN and RFNN, we know that E is less than R. Yes, I do know that. E is less than R. From HRN and HRF, we know N is less than F. Yep. From HRF and ER, we know H is less than E. Yep, that's this part. From ER and ENN, we know R is less than N. Okay, so that's all the rules we can get. So we can only look at, yeah, so, and just for simplicity, E is less than R. So now we can kind of think of it like a graph. So we know, I guess if we point to something that's bigger than yourself, so we know that H points to E, E points to R points to N, and N points to F. So this is, I think, the only possible solution in this example. But for instance, you might have like another rule, which is A is less than B, and then all you would get from that is A points to B. So we don't know the relationship between B and H or A and H. So it could be, one possible solution would be ABH, like that, AB, or it could be A is actually the smallest, and then B, and then all of this. So that's where at least I would say there is multiple possible solutions, is when you have a disconnected graph, or you could have it where N points to F. Yeah, it's kind of hard to represent on one line like this, but if you think of it like a graph, you could say N points to F and G, or like, let's say K, and like P. So if it points to F, K, and P, then you don't know the relationships between these, so you would just do all of this, and then you would do some random order of these. So that's another example where it could have many different solutions based on the knowledge that we get. So I'm just going to write that down. So multiple solutions when disconnected graph, or not like a non-linear graph. I don't know if linear is the right term, but I guess like linked list graph, because this is basically just a linked list. But whenever you introduce children, yeah, what if you had like H, and you have A, and then you have like B, and H points to A and B, and A points to B. So if there's like a line like this, and a line like this, and a line like this, with down, right, and right. So in this case, H is bigger than B, but we need to do the A first. So we kind of would have to like take the longest path of information that we can. Yeah, so that's kind of hard to know. Yeah, or if there's like something in the middle as well, like if this points to Z, and then Z points to D, which also gets pointed to by B. So is this would be fair. I also want to say too, so the only time you have an invalid solution is when there's a cycle, in my opinion. I think that's correct, because if A is bigger than B and B is bigger than A, then that's not possible. And if you were to graphically represent that, it would look like a cycle. even if you add in another element, it still would not make sense because B can't be bigger than C if C is bigger than A. Yeah, so if there's a cycle, then you know it's invalid. With this case, yeah, so H is bigger than A and B. So Z and B are bigger than D. So you know H is the biggest. H is bigger than B, which is bigger than D. So I know D has to be last for sure. So I think you could say, like in this case, I think you could say HABZD, or you could say HAZBD, or HAB, or just sorry, HBAZD. I think these would all be fine. As long as A is before Z, H is before A, and B is always before D. Yeah. So how would you do that algorithmically? I'm just thinking, so like we could just pick a random way to traverse and go H, A, C. There's no problem in doing that. But the second that it splits off, maybe it's better to like breadth first search it, so you can just do H, A, B, and then, well, when you see D, you have to acknowledge, it's kind of like a requirements, like the course schedule problem, like the prerequisites and everything like that. You need to just find a path where that all the prerequisites are met. So what if you breadth first search from the element, like the other way around? So what if you'd start with D, and then you could breadth first search from that one and say, okay, we could take ZB, and then A, H, and then it would just be like H, A, B, Z, D, which is a valid response. Because it's like, we can imagine these as prerequisites, like the course scheduling problem, where we're given this alien language, and then we boil them down to, like, if you think of it in terms of a class schedule, like class H must be taken before class E or something. Then we have to return a valid sequence of classes. So I think with problems like that, and what it would make sense to do is start with the one that blocks up everything else. So you'd start with D, and then, to me, breadth first search just seems more intuitive, because if you do depth, yeah, I'll just assume breadth first search just because it kind of more slowly incorporates. So, okay, so if we look at, this example is just linear, but yeah, something like this. What if B, okay, so now what we're going to do is point to the one that's bigger than you. So these will all point up. And then if we have something like this, so now this graph has multiple nodes with a, okay, so if we, let's assume graph, so graph points to nodes bigger than it lexicographically. Letter nodes point to, okay, nodes point to other nodes bigger than it lexicographically. So F points to B, that means, so like our rules in this case, so first what we're going to do is take this and dilute it into the rules. So just to have like a general flow of what we're going to do is using input get rules, and then using rules build graph, and then using graph determine order. I guess determine valid sequence. Okay, so that's the method. Okay, so I started backwards, so now I'm trying to think like, so if it points to nodes that are bigger than it, then we know that A is bigger than H. We know that B is bigger than H, Z is bigger than A. D is bigger than Z. D is bigger than B. And F is bigger than B. So yeah, and then when we draw it, it looks like this. Right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. So when we draw it, it looks like this. And then yeah, we also have to do like the cycle check and stuff like that. And we can do that by just having a visited set, and then if we reach something that's already been visited, then we know there's a cycle. So I think what we'll do is, well, not necessarily. I think what we'll do is probably start from a node which has, so we have to know all root nodes. And when I say root nodes, I mean nodes with 0 in degree. So there are no nodes pointing to it, which means that nothing is smaller than it that we know of. So in this case, it would be F and B. So these are the ones that we have to like start at. Yeah, so those are definitely going to be in the front. So of our answer, those are definitely going to be in the front. Sorry, it's F and D. I'm going to change, no, I can't. Let's do F and D. So those are going to be in the front, but I'm thinking if we look at just F, we would basically breadth first search it and get FBH, which is a find rule. And then for D, we would get DBZAH. Right. So how would we combine these? Well, they're kind of like independent. Well, they're not, because B and H are in both of them. Yeah. This is hard to do on a Google Doc. Or not a Google Doc, but just like a text editor. I need to think of... Yeah, alright. So I don't know if I'll be able to... This is a big problem. I don't know if I'll be able to solve it. Namely because I can't really remember how to even do a cycle check, which is part of the problem. But also, there's just a lot of things to consider. So I'd be happy if I could just boil the problem down into different graphs, I guess, that like represent an issue or a case that can help me get to an algorithm. Because I see... So this rule, so D is less than B and F is less than B as well. My question is, like, can we just put it in visited? Maybe we have to add another edge. if we have two of these, then we know that they can come in any order, right? So if you have two nodes with an in-degree of 0, then that means they can come in any order. So this is important, this edge here, because in this case, because D covers all of them, I was thinking, okay, we can just point F to D and then do D, breadth first search from D, and that'll get everything. But if this isn't here, we can't do that. Because D doesn't cover everything now. But in this case, it would be, so it would be DZAH. And these would be completely independent now. So we'd be able to just kind of plop one on top of the other, and it wouldn't matter. Yeah. I think it's important, like, how many they share. We don't have to do it all in one traversal of the graph either. But I think maybe knowing, like, how many children the roots share. So, yeah, there's two big parts of the problem. I would say this is like the first part is using the input build the graph, and the second is what you do when you actually get the graph. So maybe for this episode, I could try just building the graph. And then maybe I can, like, I don't know, look up a solution video or something, because I feel like this will be a difficult one to understand. Just because there's so much to consider. Like, this edge adds so much. So, okay. So in this case, D, I'm not really sure why, but I feel like knowing what they share is important, because if they don't share it, then you need to, like, okay, so I know when I see F, I know that F and B has to be covered by F. Like, we need to have F and then B. And then H can come whenever, because it's shared. So it's like we have to complete all of these. So it's almost like when you find something that has multiple prerequisites, you have to kind of do each completely. But of course you can, like, nest this into something else. So what would that look like? Let's say if H connected to X, which also connected to Y, which connected to, I'm just going to change these. So if you have something like this, and just to make it more generalized, so I'm kind of just like inventing a graph and then seeing where that takes me. And yeah, okay, so I think for this one, I'm going to use Paint which you're not really allowed to do in interviews from my understanding, but I think it'll just help me like draw out what I'm trying to say so I don't have to do like ASCII art. Okay, so we have U, W, X, Y, Z, because I need to do arrows for all of them too. So we're pointing to what's bigger than it. So I'm going to assume it's like this. And then F, A, D, E, B, C. So if this is the graph that we've made from our rules, yeah, so if this is the graph that we've made, a couple key things is we know that these are the smallest and this is the biggest, but we could also have this. My question is like, is it possible? Like, we don't necessarily know what the biggest is because we could have something like this. So why don't I just keep it like that? Do we always know what the smallest is? I think there has to be, if it's possible, like it has to have at least one. Because if it doesn't have at least a 1 with an in degree of 0, like this is all fine, but one of them has to have at least an in degree of 0 because, or else there'd be a cycle somewhere. No matter like, okay, let's say this is the graph. If one of them points to Z, no matter which one it is, then it will be a cycle. So we can't assume that there will be one with an out degree of 0, but we do know that there will be one with an in degree of 0. So I'll just add this. So I think that's like a reasonable place to start. And there could be multiple. So that's definitely a conclusion is, I don't know where I'm writing all of this. I guess I don't need this anymore. There must be at least one node with an in degree of 0. To avoid cycles and be possible. So if there is just one, then I think the problem isn't bad. Well, okay, so if there's just one, right? So if there's just Z, what happens if we breadth first search from Z? So we could do, we do Z, and then we could do X, and then we could do Y, which, so if this is the smallest, then this would be wrong. So we also have to account for this. So it's kind of like we can only add U if all of your prerequisites are done. So maybe Z. So, okay, so we'll add Z, and then we check X, but X's prerequisites are not all done. So we would go to Y, because Y's prerequisites are all done. And then from every neighbor, we check, are their prerequisites all done? So X's prerequisite is all done, so we can add X now. C's prerequisites are all done, and so are E's. Okay, so we'll have like a Q. So the Q is just Z at first. And then we add its neighbors, which I guess would just be Y. And let me use a nicer color like blue. So we have our Q, and then, so we pop Z and add its, and then we also have like our final path answer. So I think that's whenever we pop from a Q. Yeah, I guess I'll just say that's like when we pop something from the queue, we add it to the answer. So we pop Z, and then for all of its neighbors, we add them only if their prerequisites are already met. So X His prerequisites are not met, so we don't add it to the queue. Y's are though, so we add Y. And that's all of Z's neighbors. So then we go back up to the queue, and we pop Y, so we add Y to the final answer. And now for all of its neighbors, we check if all of its prerequisites are met. So X's prerequisite is all met, so we add it to the queue, C as well, and E as well. All of their prerequisites are met. So now we'll pop X, so X will add to our answer. And so get rid of X. And then we'll add W, all of its prerequisites are met. No, it's not. Not all of W's prerequisites are met. So we don't add it because it has this one. And same with U, we don't because this is not. So then we just do nothing. Now we pop C, add it to the queue, or sorry, add it to the answer. And then all of its neighbors. So B is good. Also, I shouldn't have added E because E's prerequisites are not met yet because of this one. So X was correct. We popped X. E, I just removed. So C was correct because it has no prerequisites. B has no prerequisites, or I guess I should say all of its prerequisites are met, so we'll add B. And E, all of its prerequisites are met now because C has also been added to the result. So yeah, whenever we add something to the result, we'd have like a counter for all the nodes, which would have the number of prerequisites. Okay, so we add B, and now we can add E because E is good. Right, so now we pop from the queue. That's B, so we add B. And now explore all of its. So we can't add F to the queue because it has this unexplored, unsatisfied requirement A. So we just end it there. And now for E, we pop E, add it, and then add D because it has no requirements. And then do that for D. Add A because it has no requirements. And so on. So then we add, we just popped A, so now we add F because its requirements are both fulfilled now. When we added A, this counter went down to 0. So now we have F. Okay, then we pop F, and that makes U's counter go down to 0. So when we explore it as a neighbor, it's now 0. So we add it. Or sorry, this is a W. So W, we add W, and then we'd add U now, it has nothing, so then we'd add U. All right, so that looks good to me. I could implement that for sure. And then this is our final answer, Z, W, X, C, B, E, D, A, F. So this works when there's 1. So basically what you do is just breadth first search and only add things to the queue if all of their requirements are met. So I'm going to write that down. If there's one root, I'll call it BFS, but only add to queue if all prereqs are met. I guess all are already in answer string. Okay. What if now then we have this. So now we have 2 nodes with an in degree of 0. And what if I put it here? So my initial thought is we just add them both to the queue. We add Z and E. And then we would pop Z, but then Z would have none of its neighbors. So I think what you do is, if you pop a root and it's invalid, maybe you can just add it to the end. Because we would have to, we'd have to explore Z again. Because, yeah, well, maybe you don't have to do that, actually. So if we add both of them, let me get rid of this. So you'd pop it and add it to the answer. So you add Z to the answer. And now that actually makes all of these prerequisites go down by 1. So then by the time you pop E, you're actually ready to add Y and D. And I think that's fine. Yeah, I think that's all right. Okay, so I'm wondering if that just like works. Is you just add it to the queue if all of its prerequisites are met. Let's try it on the test case example. So we had, and remember we're pointing to the bigger thing. So let me go down here. So N points to F. H points to E. R points to N. And E points to R. So in this case, we would identify R as the root, one of the roots. So we'd add all the roots, which would just be H. And then, so we'd pop it and add it, and then all of E's prerequisites are met. So, and then we would just continue that. Yeah. All right, so I could try doing that. So we would need to definitely identify the roots and identify the requirements for each one. Yeah, so that's this part. And that's without the cycles. Okay, so I'll just write some pseudocode. So init queue to contain roots of graph. While queue, say current is queue.pop, add current to result, and then decrement all neighbors of current by 1 so decrement I think means by 1 already. So we'll decrement the number of prerequisites of neighbors. So what I mean by that is, so if we have, let's say we pop Y and add it to answer, then that means X and C would, their number of prerequisites would go down. So yeah. All right. And then I guess we could just say for neighbor of current, decrement number of prereq of neighbor, and then if number of prereq equals 0, then add neighbor to queue. So if it has, so we'll decrement it, and then if it has no more prereqs, then we'll just add that neighbor to the queue. I think it's that simple. So the prereq dictionary, what is that going to be? That's going to have, so what is that going to look like? I'm just going to flush that out. That's going to have a node name. So for instance, like A, and then just a number. B. All right. And what is the graph? So I'll come back to this. So first, let me see what the graph is going to look like. So it's going to have a node. So in this case, it'll be Z, and it will point to everything that's bigger than it. So X and Y. And then we'll have Y, which in this case points to X and C. Okay. And every time this every time a node gets added as a neighbor, we will increment its prereq by 1. So in this case, when we have Z is smaller than X and Y, then we'd say X. So let's just imagine everything is initialized to 0. X, Y, Z, and C is what we're working with. So if everything is initialized to be 0, then when we build the graph, and these are our rules, so from the rules that we're going to make, where Z is bigger than X, no. X is bigger than Z, Y is bigger than Z, X is bigger than Y. Right, so these are our rules. So for this one, we'll say X is bigger than Z, so we'll put Z as the key, and we'll add X to the list. So that means X now has one prerequisite. One like immediate, this is kind of just like the number of in degrees. Yes, this is the number of in degrees. And then we can initialize roots as a set containing all. Roots will be easy to find. So this is kind of like number of in degrees. How many things point to me? Then we'd see Y is greater than Z, so we'd put Y right here, and then we'd increment Y by 1. It has something that it depends on. Now we see X is bigger than Y, so we'd make Y here, and we'd add X, and now we say that X would have 2 prerequisites now. And then this is the prerequisite dictionary that I'm referring to here that will decrement. And then if it's 0, then we know we can add that neighbor to the queue to be popped. All right. Okay. So now, what is the inputs? Yeah, so we need to get these rules. So how do I want to represent these rules? Probably as tuples, where we would just have like the smaller one and then the larger one. Yeah, so let's so this is like number 2 kind of this is number 3. And then number 1. So I want rules to be a list of tuples where each, yeah, and then it'll be a tuple of smaller node and bigger node. So this gives us basically a list of edges, and it gives us the relationship between the edges if we just always do smaller on the left and bigger on the right. Alright, so how are we going to get these rules? So now this is kind of a sub-problem. Given this input of sorted words, we have to return rules. So that's kind of like the sub-problem. And then, I could probably turn these into functions. Okay, so how would we get the rules? Well, I think what we do pretty obviously is we could look at the first. I'm just trying to algorithmically think. I think while the first numbers are the first letters are the same, we definitely want some sort of pointer. I think we should have 2. This part's kind of a little more complicated because what if we had HRN, HRF, and we also had let's just say HRZ. So we'd probably, maybe the first step we'd want to do is think, or I guess determine, how many of these start with the same letter. So maybe we could have like, or is it just as soon as we find 2 with the same letter? If we find 2 with the same first letter, alright, maybe we could start with the most obvious of the rules. So, which is just comparing the first letter. So we can say, okay, has the same letter, does not have the same letter. So then we have HE. That's a very simple way to do it. And then I comes here, and then you do the same thing. So has the same letter, doesn't have the same letter. So now you have E is smaller than R. And I almost wonder, like, now you can kind of recursively do that again, where, so you're doing that for those, and now you can kind of like, okay, so we know H is from 0 to 3, or I guess 0 to 2, and now we'll look at the second letter. So these have the same second letter. These have the same second letter. So now we'd look at the third letter, and these do not have the same third letter. Maybe we can do that instead. So we'll just compare the first 2. Okay, so we'll compare the first 2, and we'll say, okay, these have the same first letter, they have the same second letter, they do not have the same third letter. So we'll say N is less than F. So we've kind of done that. Now we'll move on to these. They have the same first letter, they have the same second letter, they don't have the same third letter. So additional information we can get is, if we compared these 2, we would know that N is less than Z. That could explicitly be one of our rules, but I don't know if we actually need that information. Is that, so do we need this? We kind of don't, because it's explicitly outlined here, like with the transitive property. I think that's what it is. That's like if n equals f and f equals z, then n equals z. I don't know if that applies to inequalities, but I'm wondering, obviously in this example we don't need it, but I'm wondering if there's ever an example where we would have to compare the first and third, and comparing the second and third would not be enough. Anyway, that being said, so then we'd move our pointer, so we just compared those, so now we'll compare these, and we say, okay, the first one is not the same, so we know that h is less than e. And that's all we do for those. Now with this one, the first is the same, so we check the second. The second is not the same, so we know r is less than n. Then with these, we determine, I think that's all you can really determine. You can only get one rule for any two words that you compare. You can only really tell one thing. You can't get any more information from just two words. Okay, now this, the first letter is not the same, so we know that E is less than R. I'm going to assume for now that this works, because we could so that's just like a linear scan. We could do like an O of n squared thing where we compare every combination. So we compare this one against all of these, and then this one against all of these, and this one against all of these. But I wonder if it's sufficient just to do this. Like, I don't know if we actually, I'm not convinced we need the extra rules. Yeah. But if we do, then it shouldn't be too hard to implement. So try linear scan, but can use quadratic if needed. Okay, so I'll try this. I feel like I'm at a point in the problem now, 50 minutes in, where I can start trying to do it. Or at least like getting down some scaffolding code. Yeah. So I'll just try the linear scan first. So we'll have rules, which is a list of tuples. It's basically the edges. And we'll have I and we'll have j. And then while j is less than length of words, each one is going to go up by 1. Not necessarily. Okay, so yeah. Okay, so with the first two, while so right now we have 0 and 1. I think we need 2 more pointers because we have to access each individual letter, but we don't want to lose our initial 0 and 1. Well, I don't think we need this because it's always just going to be, with the linear search or the linear comparisons, it's always just going to be this, and then this, and then this, and then this. So we can use a for loop for that. So we could say, I guess, for I in range, and we'll start at 0 and go up until length of words -1, because we want to go here. So in this case it's 5, so we do 0, 1, 2, 3. Yeah, because 4 is not inclusive. So okay, yep. So we'll do this pair, this pair, this pair, and this pair. So we'll always compare I and I plus 1. Okay, and then we'll have j and k, which initially both get set to 0. So now we're looking at the individual letters. So while, yeah, so the first word is words of I, and the second word is words of I plus 1. And we'll say while the 2 pointers, and maybe we don't even need K. Because, yeah, I don't think we even need K. Because they'll always be 0, 1, 2. I don't think we need to change that. Okay, so while they're equal, we want to increment J. And then whenever they're not equal, that's where we get our rule. So if they don't equal, then we will append to our rules a tuple, which will be the smaller word. Yeah, so how do I know the smaller one? When they're not equal, the smaller one is the one on the left. So words I, J, words I plus 1 and J. So if they're not equal, then we append the one on the left first. All right, and let me print rules. I think that's everything that we would want. And this is, okay, so here we have n is less than f, h is less than e, r is less than n, e is less than r. Okay, perfect. So we've gotten the rules. Hopefully this is enough. We could also do the quadratic search where instead of just comparing I to I plus 1, we could have these be 2 different pointers. Quadratic. Okay, quadratic. All right. So now we have rules. All right. For rule in rules, we want to build the graph. So the graph will be a dictionary, adjacency list like this, and the prerequisite dictionary, I'll just call prereq, will just be counts. Prereq counts. I'll just call it prereq. Prereq. All right, so for rule in rules, what do we want to do? Let me get rid of this. So what is rule? It's a tuple. Yeah, so let's say smaller, larger. If smaller not in graph, then we'll say graph of smaller equals empty list, and then graph of smaller dot append larger. Yep, and then at this point we want to say prereq if larger not in prereq, then we'll say prereq larger equals 0, and then prereq larger plus equals 1. Whoops. So these are the prereqs, and then this is the graph itself. So let me try printing that. Seeing if that looks right. So yep, 0 has 1 prerequisite, and then also I should probably add the smaller. Just so we don't miss that. I'm trying to think, do we need to know if something has no, if it's not in there, do we need to know? so for instance, the largest element, let's say it has no out degrees. Do we need to know that? I don't know. I could just add it if we do. I don't see why we would need to know it though. Okay, Z has 0. Then, yep, so H has, so H would be where we start, and then these are the degrees. Okay. Right, so that looks good, at least for these. So now we want to do this part. So what we'll do is, so we initialize both of these. We need a queue. From collections, import deck. We also need to identify the roots. Yeah, so let's just do like a little list here. It'll be x for x in prereq. All right, so I'm just going to do list comprehension. So items gets us the key and value, and I'll just say if value equals 0. This is like the number of, so this will be an element and the number of prereqs it has. So if the number of prereqs is 0, then we'll have roots. So what we want to do is make a queue, which is collections.deck, and that will contain within it a list of roots. Right, so now the queue just has roots in it. Whoops. Press and hold escape. All right, there we go. Honestly, that's kind of nice. Should I do this? Okay. All right, so now while the queue exists, we will pop something from the queue. I'll just call it node. Add current, so I'm just referencing this. Add current to final answer string. Yeah, so when we pop, so we'll just have an empty string. When we pop, say result plus equals node. And then we want to do for neighbor in graph node. So what is this? These will just be the nodes, the neighboring nodes. We want to say prereq of neighbor minus equals 1. And then if prereq of neighbor then equals 0, then q dot append left neighbor. Yeah, and then we would return the result string. Okay, so that was a bunch of stuff. Let's see what happens when I run it. Okay, so node, what's in our queue? I think I'm doing a list of lists by accident because roots is already a list. Okay, for neighbor in graph of node. Yes, so I have to do the graph.get node. So O didn't exist because it had nothing that was bigger than it. So what we'll do is just do an empty list there instead of adding it to the graph at the top. Okay, so it worked for these. Those are pretty simple. It's going to fail definitely for if there's a cycle. This is the very first test case. So it passed those two. Those ones are pretty easy. So let's look at this one. A, B, C, B, C, D, C, D, E. So we know A, let me print out my rules and see if it aligns with what I would think as a human. So A is bigger than B and B is bigger than C. So I'll put A, B, C. Okay, but we also have E and D. So E and D have no rules associated with them. So they have no rules associated with them, like we can't really tell the relationship, but they still have to be in the answer somewhere. I think if we put them at the end, so I think A, B, C, E, D is also, or A, B, C, D, E is also valid. So we'd have to also just add them. We need to know like unused. Yeah. We'd have to know the unused words for sure. So a simple way to do it would just be like, actually, let's say for word and word. So this would be a really easy way to do it. I could clean it up if it works. We'll just have like all letters. For I in range length of word, say all letters dot add word of I. And then whenever we find something in a rule, yep, so this would just basically give us a set of all the letters, and then whenever we find something in a rule, we could just all letters dot remove words of I, J, and all letters dot remove words I plus 1 and J. So all letters in this case should just be D and E. So it's really unused letters. B. So B. What happened? It's trying to remove it twice, maybe. Yeah. So if so yeah, it's kind of like a sloppy workaround, but all right, yeah. So then, can we join? I don't know if you can join a set. Okay, you can. All right, so let's see. It'll fail still, but right. Yep, this is another good test case. So in this case, they're equal, and then it goes up. So what do we gain from this? Do we gain any rules from this at all? don't think so. This doesn't tell us any rules. WRT, KJ, and WRT. Yeah, so in this case, we would just kind of skip it, I guess. Yeah, so first of all, we have to do the out of bounds check. So probably say like while j is less than length of words of I, and j is less than length words I plus 1, and test case probably need parentheses. Missing a parenthesis. Length. Okay, so in this case, j is 2, and then you add 1. Right. And then here we'll just, if j equals length of words of I, or j equals length of words I plus 1. So if it equals either of them, then we don't want to do this. If it equals this or it equals this, then this will be true. Okay. What if it equals, so if it equals one of them, then it'll be true or false true. Yeah, and I think that's the behavior we want. Still out of range. So this one is, the order is invalid. Oh. So is this an edge case? Like this is weird because, so it's invalid because the shorter one has to be first. So if we exit out prematurely, well, maybe I should just say this. If it exits out prematurely, then we just want to continue to the next word pairing. But also we just have to make sure that, or let's say if length of words of I plus 1 is less than length of words of I, then we have to return an empty string. I don't know if there's anywhere else. Yeah. Yeah, it's like super. It's kind of rough around the edges, but basically what it's doing is this checks if we exited because of this. I don't know if there's like a better way to do out of bounds handling, and I think maybe it's like the while else statement, where maybe we could just say like if j is greater than or equal to this. All right, so that works. I'm gonna try it this way. While j is greater than or equal to that, or j is greater than or equal to the length of words of I plus 1, then we'll break. And then I think the while else statement only handles when it breaks. Like that. Yeah, so we don't need this anymore. So maybe the else statement only handles if it. Sorry, this is a bit of a detour, but I just want to see. Breaks. Oh, but now continue is inside the loop, right? Yeah, because I want to go to the next for loop iteration. I don't know, this is interesting. It could be this like return statement. So in case 1, it's executing the else. In this one, it's not. So I think it's if you don't break. So else always gets executed unless you break. So in that case, would I benefit from putting this inside the else? Yeah, I'm just going to keep it how it was. I'm not knowledgeable enough about that. And it's not like super bad or anything. Okay. Return like that. So this way was working. Okay. Let me see where this would fail next. Okay. So this is probably one that has a cycle in it. So we have these unused letters and this. So what did I return? So let me print what result is. So result, I'm guessing then is empty string probably. Standard out, yeah, empty string down here. Okay, so we have M goes to N, N goes to O, O goes to P, PQ, QR, RS, ST, TU, UV, VW, WX, XY, YZ, ZM. Okay, so here's the cycle that we have. So I wonder how I can detect. So, okay. So I feel good about everything else that I did. I mean, this is like probably better ways to do this, but yeah, when it comes to cycle detection, I'm wondering for this specific problem, I will say we never pop the same thing twice. So if we have like with this algorithm, so maybe if we pop the same thing twice, we know, because we have like A, B, C, and then C goes to A. Well, also there's nowhere to start, right? So it just never starts, right? I mean, that's one way to tell for sure. Yeah, I mean, one way to tell for sure is if length of roots, I guess if not roots, then that's one way to tell for sure. If there's no nodes, yeah, but this will fail because there's still, I don't know what that is, but so you could have this, and there is still a root, but this would fail. So I'll just write down like for cycles, maybe popping something twice can detect it. What about this one? We have ZZ. My output is nothing, so return null. Okay, so I want to see why it's returning nothing. I didn't use it as a test case. All right. So return null 2. So it has no roots. Why is that? Well, okay. So it has no roots because it has no okay, what is this? So it's basically Z and Z. So this will say there are no rules either. There are no rules. Yeah, all letters and rules. So there are no rules, which means of course there will be no roots. If there are no rules, then let's just return. If there's no rules, then we can just return all letters by itself. So that will fix this one. It's still not, it didn't. Yeah, I gotta join it. Gotta make it a string. Yeah, so there's no rules. So that's, okay, it's still gonna fail. Okay, we're getting through a lot of them though. Okay, so expected, okay, so maybe this is the, like, this case here, where we have a cycle. Basically, I haven't done a true cycle detection yet. Alright, so we have J, I, IH, HG, GF, FE, ED, DC, CB, BK, KL, LM, MN, MO, OP, PQ, QR, TUV, WX, YZ. Alright, so I see we have a cycle here. So J goes to I and I goes to J. So that's definitely a cycle. We also have repeated rules as well, which is interesting. Yeah, so we have J and I right here, and then I and J. So this is impossible, and it has a cycle. But there's probably some that exist. Also something too, yeah, like I said, we have a KL here and a KL here. So I wonder if rules should be a set of tuples. Can you have a set of tuples? I think so. Because tuples are immutable. So what if I make rules a set? And then I say rules.add. Does that like crash? No, okay. So I'm gonna make rules a set just so we don't have duplicate rules. So my result is A, but it should be nothing. And that's because A is probably a root. Because there's nothing that has A second. Alright, so let me print the graph here and maybe I can draw out a simplified version of it. Graph doesn't exist yet. Right. Okay, so print the graph here. Alright. So I'm not going to draw out the whole thing, but I do want to see the gist of it. So I'm guessing A is not even in there. No, A should be in there. Because the graph is pointing to things that are bigger. So A should be in here. And it should point to J and I. Yeah. Or it just points to B. A points to B right here. Oh yeah, I guess that's the only thing that you know. Because J isn't necessarily bigger than I. Okay. Okay, so we have A points to B. And then what does B point to? B points to CK. And then does K, what does K point to? K points to L. What does C point to? C points to two other things that don't matter. Well, let's see what K points to. K points to L. That's it. Oh, so where is the cycle? Okay. So A points to B. B points to CK. So I'm just going to write out like a little bit. CK. C points to DB. Oh, that's a cycle. Okay. Yeah, that's fine. All right, so C points to B. All right, so let's just consider this graph. So this is invalid. So we'll have A is in our queue. We'll pop A, so A will go to our results, and then we will see are all of the prerequisites met of B. The answer is no. Okay, so to have a cycle means that the prerequisites will not be met. Right, because what if we have A points to C, which points to B. B also points to C. Yeah, so the thing is, this cycle will never be met because they both have an in degree of 2. So I think maybe a way around it would be we just keep track of the number of nodes that we visit, or I guess that would just be the result. If result doesn't equal the length, so like, what are all the nodes? That's the all right. Okay, so we actually do need to know all of the nodes. So what I'm going to do for that is we add, where do we add the rules? The graph right here. What I'm going to do is also add the larger, which means that we don't need the dot get thing. So graph. So the length of graph is the number of nodes. That is true. So if the length of result doesn't equal the number of nodes, then we know there's a cycle, I'm pretty sure. Because in this case, we basically the result is essentially like a visited set. So we need to visit every node. If we can't visit every node, then that means there's a cycle. So in this case, result is A, but the number of nodes is not equal to 1. So maybe here I could just try that. So if length of result does not equal length of graph, then return empty list. So that will definitely work for this one. Will it work for others? Okay, yeah, it does. All right. So I actually got it accepted. Wow. That's awesome. I'm really happy about that. It did take 1 hour and 30 minutes, but it is a hard problem. Let me try to pull it up on LeetCode and see if this works. So it's called Alien Dictionary, because the one I did earlier today with like the Dijkstra's but only K moves, K flights, that one did not work on LeetCode. And it feels kind of illegitimate unless I also get it on that website. All right, so let me pull it up here. Would I recommend LeetCode? Would you? I don't know what that is, so I'm just gonna X that out. Oh, it's locked. All right. Guess I won't know. Okay, but I do want to clean up the solution a lot and maybe think of some better ways to do things. I think this is fine. Okay, let me start from the top. So I don't know if there's a better way to get all the letters. It doesn't give me that, right? So I'm just going to change this to letters because... And is there a better way to do it here where... Like, I'm surprised this... I feel like this should be in one line where you just like remove it if it's not in there. Make a note. Is there a smarter way to do this? I mean, we need all the letters, and then I'm just thinking like, yeah, my idea is if there's unused letters, you can just you have to add them in the end somehow, or in the beginning. It doesn't matter, but you have to add them to your answer. This is a good way to check for cycles. This, I might not need this anymore. Because roots, it'll just skip all of this. And if there's no roots, is it possible that the length of the graph will also be 0? That means there's no rules, but we already have an edge case for no rules, so I shouldn't need that. Let me just verify that. All letters. Where do I use all letters? Right here. All, okay. So let me verify. I'm pretty sure I won't need it because of what I said. So the only case I would need it is if this is actually true. And for that to be true, so this will always be 0. So that means for that to be true, this would have to be 0. And for the length of the graph to be 0, we would need no rules. But I already have an edge case for no rules. So we don't need that. We don't need that print statement. This part seems fine to me. this is like the cycle check. Do I need this? I need this at the bottom because we build result here. This is odd. I just don't like this. Yeah, I just hate this. I just hate this whole thing in general. Don't need that. Yeah, this part sucks. This part's fine for building the graph, I think. I could use like a default dictionary. That would definitely cut down the line count a lot. But this is important to do, and a default dictionary would not capture this behavior. I forget why it's important. Oh, it's so that we can get the length of the graph to do the cycle check. This is fine. Can I do it earlier? No, because this creates the rules. Yeah, this part just sucks. This part is fine. I'm just going to add some comments. So this is build graph using rules, and then this is use dependency graph to get valid sequence. Yeah, this part just sucks. Okay, so I'm happy with everything else. I mean, this is kind of like a workaround. The only way to get all the letters, though, is you would have to do this. You can't do anything about this. I mean, maybe I could use like list comprehension, make it look cooler, I guess, but yeah, I mean, not to look cooler, but to take up less lines on something that should be easy. But it's not really a list comprehension thing. Yeah, it's not really a list comprehension because we don't want a list. So yeah, we'll just do that. That's fine. Yep, I want to do that in one line. I feel like there should be, it's kind of like the dictionary.get type thing. Like if it's not there, then just return a default value. Like this, I don't know. I feel like, because with adding it, right, when you add to a set, you don't have to check if it's already in there. So I feel like the same thing should happen with remove. And maybe it should just like return like an optional, like maybe this could return if it was there or not. I don't know. Okay, so with this one, what do I need to do? It's just, this part's ugly just because of the edge case where if it's like two words and they're exactly the same except one of them doesn't have the last letter, and they have, this part checks if they're in the right order, and then we do want to continue because we don't, yeah, like we don't want to, I mean, it makes sense why it's like that. I just, like, it just looks so ugly. Maybe I'll just add comments. Have same letters, but different lengths, i.e. ABC and AB. Make sure smaller word comes first. Yeah, I also just want to note, like, I'm going to look into while else statements. Just because I feel like this happens to me a lot where I'm doing something, but I need to make sure a pointer. So I'm in a while loop and I'm incrementing a pointer, but I need to make sure it doesn't go out of bounds. But I need certain behavior if it did go out of bounds. And I'm wondering if while else is like the right way to do that. Yeah. I think that's. I didn't really change anything. I just got rid of useless thing of code. And then just added some comments. Okay, awesome. Yeah, I did a hard graph problem. I think that's my first hard graph problem that I did. Yeah, I'm happy with that one. I wasn't sure I'd be able to do it, but I'm glad I did it. Yeah, really happy about that. It's good to know that some hard problems are like in my reach. Yeah, still have a lot of dynamic programming that I should get through. And I know nothing about bit manipulation, so I should probably do that. But anyway, long episode today. Thank you guys for watching. That was day 90 or episode 93, I think. So I'll be back for 94.